Hey class, this is Mr. Durst, and we are going to be having a discussion in this video about PhysioEx exercise number 6, which focuses on cardiac physiology. It was brought to my attention just a little bit ago that the initial video I recorded using your lab manuals cap graph wasn't actually that helpful. There were some ways, I got some really good feedback from some individuals about ways I can make it better. And since it's still before Monday, I'm redoing this recording. We're giving you a clearer one, and I hope you enjoy this refined recording. So without any further ado, let's dive into it. As we look at our cap graph is going to focus on cardiomyocyte action potential. So CAP stands for cardiomyocyte action potential. And this cap graph is going to be broken up into three phases. I'm going to start at the beginning, phase number 4, because I'm a pretty linear guy, and I also like resting potential. So as we look at phase number 4, during phase number 4, we have potassium ions that are constantly leaking out of the cell from the intracellular fluid to the extracellular fluid. So the inside of that cardiomyocyte is losing positive potassium ions. And while that cardiomyocyte's losing positive potassium ions from the inside, that cardiomyocyte is eventually going to reach threshold and spontaneously induce its own action potential. Now these cardiomyocytes, these just regular heart muscle cells, they don't do this with a high frequency, so these regular cardiomyocytes aren't going to be the cells that dictate the overall heart rate. They don't determine, they aren't the pacemaker cells. But be advised, they will spontaneously depolarize at a low frequency. They'll spontaneously have their action potentials initiated. So we're just having a little potassium leak out of the cell, and then we have, boom, right here at phase 0, we reach the threshold voltage, and that threshold voltage causes sodium voltage gated channels to open, and this is very fast. Sodium ions are rushing into the cell, and as we have sodium ions rushing into the cell, that's going to cause the voltage on the inside to skyrocket, and the voltage goes up. And then at this point, we have a little bit of a steep downward turn. And at this phase 1, the steep downward turn, we're still having the potassium leak channels. We're always having those potassium leak channels leak potassium out. However, the potassium leak channels don't account for this peak, that's downward spike. So there are a couple other things that are going to happen at this peak. First, the sodium voltage gated channels close. Second, there's a special kind of potassium voltage gated channel. There are 2 different kinds of potassium voltage gated channels, the primary one and the secondary one that we care about in this graph. And the secondary potassium voltage gated channels opens and closes very quickly and gives us a little bit of steep downward slope. So that that secondary potassium voltage gated channel opens, closes, and gives us whoosh, that little downward slope. And then we're going to continue having leaky potassium leak channels, still constantly leaking potassium ions out the entire time through phase 1, phase 2, and phase 3, and phase 4, the entire time. Something else happens though. We have an L-type calcium voltage gated channel, or long-lasting calcium voltage gated channel, open at this peak. And that's going to cause calcium ions to move into the cell. So we're having calcium ions move in from the extracellular fluid to the intracellular fluid, and that is going to continue while potassium is leaking out. And that influx of calcium causes this plateau phase at phase number 2. And this plateau phase is going to extend the absolute refractory period, this period of time where the cardiomyocyte cannot have another action potential initiated. Eventually, though, the long-lasting calcium voltage gated channels close, and enough potassium has leaked in to lower the voltage to another key point. And at this key point right here, the voltage change will cause the primary potassium voltage-gated channels to open and cause the long-lasting calcium voltage-gated channels to be all closed. And when this primary potassium voltage-gated channel opens, we have rapid repolarization during that phase 3. Towards the end of phase 3, we have a little triangle right over here that represents this period of time. This period of time right here is the relative refractory period. So if we combine our absolute refractory period, where it's physically impossible to induce another action potential, with a relative refractory period where we can, if we have a very strong stimulus, they combine to give us a total refractory period. Pragmatically speaking, this means that for time, we're looking at about from this point to this point, we're looking at about 300 milliseconds, which means that the fastest our heart can beat is about 3 beats per second, or about 1/3 of a second-ish, depending on your health. If you're really healthy and young, it's about 1/4 of a second. For the absolute refractory period, older folks, is about 1/3 of a second for the absolute refractory period of these cardiomyocytes. And this means that we have a maximum heart rate, typically of about 240 if you're young and super healthy, 16, 17 years old, or of about 180 if you're more geriatric and more towards the silver-haired end of the spectrum. In terms of looking at the cell, here is a viewpoint of the cell to give you the overall idea. So here's our cell. We have the intracellular fluid and the extracellular fluid and this circular cardiomyocyte. I know, very artistic looking. And the overall trend is that potassium ions will go out and that sodium and calcium ions go in during these cardiomyocyte action potentials. Let's go to our next slide. This is a pacemaker potential slide. And as we look at this pacemaker potential, this pacemaker action potential is going to be located in the sinoatrial node. And I remember as a younger student, when I was a younger student, I was really confused by the sinoatrial node. I thought the sinoatrial node was made up of neurons. And I need to clarify, the sinoatrial node in the right atrium is not made of neurons. It is made up of cardiomyocytes that depolarize, rapidly. These cardiomyocytes have the highest frequency of depolarization. So these are just special heart muscle cells that depolarize at a higher frequency than the rest of the heart. And these heart muscle cells are called the pacemaker cells. And something we need to emphasize with these pacemaker cells is that there is no resting membrane potential. There's constantly changes in voltage. So as we look at these pacemaker cells, we'll start off at the downward spike. We're going to have slow influx or inflow of sodium. And as that sodium is slowly moving into the pacemaker cardiomyocyte, or the pacemaker cell, eventually we reach a threshold voltage where calcium voltage-gated channels open up. And this is going to cause a rapid influx of calcium ions. And the voltage skyrockets up. And then at peak voltage, we have the calcium voltage-gated channels close and the potassium voltage-gated channels open. Potassium ions rush out and the voltage drops back down again. And eventually, at the lowest possible voltage, potassium voltage-gated channels close, and we will have that slow inflow of sodium, causing the voltage to slowly go back up again to threshold. So these special pacemaker cells, these special cardiomyocytes that are the pacemaker cells, are going to spontaneously depolarize at a very high frequency, and thus will dictate the entire rhythm of the heart, the overall resting heart rate. Let's move on to our next slide. So what we end up happening is in the right atrium of the heart, we have a pacemaker cell rapidly depolarize, and then that pacemaker cell is directly connected to a normal cardiomyocyte, which is next door. And it's directly connected because they have the gap channels that are in the intercalated disc. Remember, think of your cardiac histology. We have intercalated discs connecting one cardiomyocyte to the next cardiomyocyte. So because the pacemaker cells have the highest frequency of spontaneous depolarization, these are considered the autorhythmic cells of the heart. And these other cardiomyocytes, because they have a much slower rate of spontaneous depolarization, they don't determine the heart rate, so we consider them non-autorhythmic. And what ends up happening is as that first pacemaker cell depolarizes and has an action potential, that action potential will immediately go next door to a cardiomyocyte. So we go from a pacemaker potential graph to a cap graph. And then we go to another cardiomyocyte with another cap graph, another cardiomyocyte with another cap graph, so on and so forth, until the entire chamber has a wave of contraction move through it, the entire chamber of the heart. So as we look at these pacemaker action potentials, the membrane potential is going to be dictated by the movement of ions. So as we're looking at this slow upward portion, we have T-type calcium channels open. Those T-type calcium channels aren't the primary force that's going to cause that steady depolarization. It's primarily going to be the sodium leak channels, although the slow influx of calcium here does help as well. We also have long-lasting calcium channels open as well. So what we see primarily is that we have a little bit of calcium get in from the T-type channels, and then when we reach threshold, those T-type voltage-gated calcium channels close, and then the long-lasting types open, and then we have a rapid influx of calcium from the long-lasting L-type channels. As we look at potassium, we find that when the potassium leak channel or potassium voltage gate channels open at peak voltage, we then notice a rapid influx or increase in the amount of potassium that gets into the cardiomyocyte, that pacemaker cardiomyocyte. Now, if we look at just a regular cap graph or regular cardiomyocyte, that's just not special, just a regular heart muscle cell, nothing special about this one. What we find is that we have a rapid influx of sodium that corresponds to the depolarization. We're going to have potassium leaking in, and then when we hit that peak voltage right here, we're going to actually have, during this plateau phase of the cap graph, potassium is not moving into the cell that quickly. There's still a little bit of influx, though, of potassium, just not that much. And then once we exit the plateau phase, we have potassium rushing into the cell very quickly when the primary potassium voltage-gated channels open and potassium rushes in. It's also worth emphasizing that during the plateau phase, just to reiterate again, that plateau is because of the long-lasting calcium voltage-gated channels that have opened, and while those are open, we have the influx of calcium ions skyrockets, lasts for a while, and then pitters off. When we reach the threshold voltage, that closes the long-lasting calcium voltage-gated channels. So if we look at the action potentials and how the charge changes, the conductance changes of the ventricle, what we find is that when sodium is rushing in, the voltage goes up. As we're moving calcium in, that's going to prolong the elevated voltage. And then when we have the movement of potassium, that's going to cause the decrease in voltage. And we're looking at about from here to here for that absolute refractory period of about 250 milliseconds. I'm not super hung up on the time. If you think 200 versus 250 versus 300 milliseconds, that's okay. What I want you to keep in mind is perspective. We're looking at a maximum heart rate of 3 to 4 beats per second. About 4 beats per second if you're young and healthy, and 3 beats per second if you're more towards the silver-haired end of the spectrum or a couch potato. Or I could say a paper pusher like your instructor, Mr. Durst. Ooh, I need to hit the gym. Anyways, let's look at the movements of these ions just to help reiterate this in terms of the phases of our slopes. So we're going to have on this previous slide, let me back up here a slide for us. We had on this previous slide a cap graph. so a regular cardiomyocyte. Here we have a pacemaker potential graph, and you can tell by the shape of the graph. Make sure you memorize the shapes of the pacemaker potential graph and what ions are moving and in what direction they're moving at each point in the graph. And the same can be said for the cap graph, the regular cardiomyocyte graph. You need to memorize the shape of this graph and then what direction the ions are moving into the cell, out of the cell, and when those ions are moving. So make sure you spend a lot of time focusing on the cap graph and the pacemaker potential graphs. As we look at that pacemaker potential graph, just to help reiterate it again, we're going to have sodium slowly move into the cell while we have our slowly leaking into the cell. And then we reach threshold voltage, and we have a rapid influx of sodium, a rapid influx of potassium. We reach peak voltage, and the potassium and sodium voltage gauge channels close. The sodium and the calcium, with the C, calcium and sodium voltage gated channels close. The potassium voltage gated channels open, and then we have a rapid increase in the amount of, and the rate that potassium is rushing out of the cell, causing the voltage to go back down again. And we can take these two graphs and just line them up next to each other to help compare and contrast. On the left, a cardiac action potential graph, cardiomyocyte action potential graph, and then a pacemaker cell action potential graph on the right. So this is the same thing again, just to help reiterate this. Here's our pacemaker potential graph. We have the slow influx of sodium here. At this point, we're going to have calcium voltage gauge channels open, and we're going to have lots of calcium rushing in to help increase the voltage. Up here at peak voltage, calcium voltage gauge channels close, potassium voltage gauge channels open. That causes the movement of calcium to decrease and the movement of potassium to increase. Potassium is rushing out, causing voltage to go down. And as we look at this right here, this slow depolarization, this period of time right here is our pacemaker potential. And if we extend that slow depolarization time, we lower the heart rate. If we shorten that slow depolarization time period, we accelerate the heart rate and make the person or the individual have a higher heart rate, so that more beats per minute. Here is another graph of the same thing that looks at the different ion channels in the different phases. We've already talked about this graph in detail on a previous slide, but here's the same thing explained differently. So if you want to pause the video right now and look at the same concept explained a little bit differently, you absolutely can. And that's all we have for our recording on cap graphs and pacemaker potential graphs. If you have any questions or comments, please feel free to post them on the class discussion board. And as always, happy studies.